Welcome to Inorganic Chemistry. Today, we are going to explore molecular orbital diagrams. If you have ever wondered how atoms actually stick together to form the molecules that make up the world around us, you are in the right place. We will build this understanding entirely from the ground up. Let us start by imagining two people living in separate, tiny apartments. These represent atomic orbitals, the spaces where electrons live around a single isolated atom. When these atoms decide to form a molecule, they knock down the wall between them. Their individual atomic orbitals merge to form a new shared living space called a molecular orbital. Instead of orbiting just one nucleus, the electrons now orbit both nuclei. This shared arrangement holds the atoms together like a strong glue and is the absolute foundation of molecular orbital theory. Now that we understand what molecular orbitals are, let us look at how they form. When atomic orbitals merge, they behave exactly like ocean waves. If the waves crash together in sync, they build a bigger wave. This constructive interference creates a bonding molecular orbital, which pulls the atoms tightly together. However, if the waves crash out of sync, they cancel each other out. This destructive interference creates an anti-bonding molecular orbital. This creates a dead zone called a node that actually forces the atoms apart. We usually mark these anti-bonding orbitals with a little star. Knowing how orbitals form leads us to how we fill them. As we add electrons to our new molecular orbitals, we start from the lowest energy level and work our way up, just like filling a glass with water. Eventually, we run out of electrons. The very highest energy level that actually contains electrons is called the HOMO, or highest occupied molecular orbital. The energy level immediately above it is completely empty, and we call this the LUMO, or lowest unoccupied molecular orbital. Together, they are crucial because they determine how the molecule will react with other chemicals. Before we look at real molecules, we must understand a special tangling effect called sp mixing. In some lighter atoms, the starting atomic orbitals are so close in energy that they tangle up before they even form molecular orbitals. Imagine pouring red and blue paint too close together. They blend into purple. For lighter elements like boron, carbon and nitrogen, their 2s and 2p orbitals mix, pushing the sigma 2p orbital higher in energy than the pi 2p orbitals. But for heavier elements like oxygen and fluorine, the orbitals are far apart in energy, so they do not mix at all. This brings us to a very important calculation. To figure out if a molecule is stable enough to exist, we calculate its bond order. Conceptually, this tells us the net number of chemical bonds between the two atoms. In the formula, Nb represents the total number of good electrons sitting safely in bonding orbitals. Na represents the bad electrons trapped in anti-bonding orbitals, which try to push the atoms apart. We subtract the anti-bonding electrons from the bonding ones and divide by 2, because it takes exactly 2 electrons to make one single bond. A higher bond order means a stronger, more stable molecule. Now that we have our formula, let us see this with a concrete example. We will evaluate the oxygen molecule, O2. We are given 2 oxygen atoms and need to find their bond order and magnetic properties. First, we count the electrons. Each oxygen atom has 8 electrons, making 16 in total. Writing out the configuration for a single atom, we see the outermost shell has 6 valence electrons. Since there are 2 atoms, we have exactly 12 valence electrons to place into our molecular orbitals. We ignore the inner electrons because they cancel each other out perfectly. Continuing with our oxygen molecule, we now fill the molecular orbitals from bottom to top. Because oxygen is a heavier element, we know it does not experience sp mixing. We place our 12 valence electrons into the orbitals. When we reach the very top, we have 2 electrons left. According to Hund's rule, electrons prefer to sit in empty orbitals before pairing up, so they go into separate anti-bonding pi star orbitals. Because these two electrons are sitting alone without a partner, the oxygen molecule is paramagnetic, meaning it acts like a tiny magnet. Let us visualize exactly what we just calculated. Here is the molecular orbital diagram for oxygen. On the far left and right, you see the atomic orbitals of the individual oxygen atoms. In the center, connected by dashed lines, are the new molecular orbitals. Notice the vertical energy axis on the left. We filled the center orbitals from the bottom up. Look closely at the top occupied level, the HOMO. You can clearly see the two unpaired electrons sitting in the anti-bonding pi star orbitals. This visual perfectly explains why oxygen gas is magnetic in real life. Now that we have filled the diagram, we can calculate the bond order for oxygen. We carefully count the electrons in our configuration. There are 8 valence electrons in bonding orbitals, which are the ones without stars. There are 4 valence electrons in anti-bonding orbitals, marked with stars. We substitute these values into our bond order formula, subtracting 4 from 8, which leaves 4 net bonding electrons. Dividing by 2 gives us a final bond order of 2. This physical result means oxygen gas exists with a strong double bond, keeping it stable in the air we breathe. Let us move to a slightly more complex case. We will determine the properties of carbon monoxide, CO. This is a heteronuclear diatomic molecule, meaning it is made of 2 completely different atoms. Carbon has 6 total electrons and oxygen has 8, giving a grand total of 14. Because they are different, their starting atomic orbitals are at different energy levels. Oxygen pulls electrons harder, so its orbitals start lower. Looking at the outermost shells, carbon brings 4 valence electrons and oxygen brings 6. This gives us exactly 10 valence electrons to place into the molecular orbitals. Continuing with carbon monoxide, we must remember the sp mixing rule. Because the molecule contains a lighter carbon atom, sp mixing occurs. This means the pi orbitals will fill before the sigma 2p orbital. We fill the orbitals from bottom to top with our 10 valence electrons. As we do this, we see that all 10 electrons are perfectly paired up, with 1 spin up and 1 spin down in each slot. Because there are no unpaired electrons sitting alone, the molecule is diamagnetic, meaning it will be slightly repelled by a magnetic field. Finally, we calculate the bond order for carbon monoxide. Looking at our filled orbitals, we count 8 electrons sitting safely in bonding orbitals. There are only 2 electrons trapped in the anti-bonding sigma star 2s orbital. We plug these numbers into our formula, subtracting 2 from 8 to get 6 net bonding electrons. Dividing by 2 gives us a final bond order of 3. This means carbon and oxygen are held together by a triple bond. This physical interpretation explains why carbon monoxide is an incredibly stable and tough molecule in real life. Now that we have used this theory, let us understand why it is so important. Molecular orbital theory explains things that simpler theories simply cannot. For example, older theories predicted that liquid oxygen would not be magnetic. But in real life, liquid oxygen sticks to magnets. MO theory perfectly explains this by revealing those unpaired electrons in the anti-bonding orbitals. Beyond that, scientists use the energy gap between the HOMO and LUMO levels to design new materials like semiconductors and solar panels, and even to predict what color a chemical will be. Let us summarize what we have learned today. We saw that atomic orbitals merge to form shared molecular orbitals, which belong to the entire molecule. We learned that bonding orbitals act as glue, while anti-bonding orbitals try to push the atoms apart. By filling these orbitals and calculating the bond order, we can accurately predict a molecule's strength, stability, and magnetic properties. Finally, understanding the HOMO and LUMO levels gives us a clear window into how the molecule will interact with the world around it. You now have a solid foundation in molecular orbital theory.